Hello spaghetti monsters, it's Mr. Spinelli. Today we're going to do a video on some theorems, in particular the intermediate value theorem, which I will abbreviate IVT, mean value theorem, Rolle's theorem, and extreme value theorem. Now for all of these we need to have a continuous function, but in the case of mean value theorem we also need differentiability. So that's what we'll be on the lookout for today, and we will apply these four theorems. So on the first one, we've got a function g of x on some interval, and we want to see if we can guarantee that there will be a point where g prime of c is 2. So some place where the derivative is equal to 2. So when I see I want a derivative value to exist, I should be thinking mean value theorem. And if you think of the word mean means average. So I'm trying to find a place where the average slope between -1 and 3, is there a place where that is equal to 2? So I'm going to plug these values into g, divide by the change in x, and if I plug those values in, I get 2 and -2 respectively. Divide that by a +2, and I get 2. So because this function is continuous and differentiable, which we know that is the case because it is a polynomial, then I can apply the mean value theorem. Now in this case, we're going to go ahead and find that c value. So if I take the derivative of g with respect to x, I get 2x plus 6. And I now want to set that equal to 2, which is this value here and here. So if I set that equal to 2, I get 2x equals -4, so x equals -2. Now sometimes you might get multiple x values. You want to check to make sure they are all within the open interval -3 to -1. Now -2 is, so that is the point C that we were looking for. Alright, so in the next problem, we've got a function on an interval, and we want to see if we can guarantee a y value of 0. So when you want to guarantee a y value, you should be thinking of intermediate value theorem. So for intermediate value theorem to work, I need this function to be continuous, and this function is continuous everywhere except for one point. So we could say it's continuous on the interval -infinity to infinity, excluding -3. This is one way you could write it. If you study set theory, there's some interesting ways you can write things more conveniently. Now what I need to do is plug in my endpoints. So I'm going to evaluate this function at -2 and then again at 5. So when I plug -2 in, the -2 over -2 plus 3 gives me a -2. Plug in 5 and I get 5/8. So sometimes you may look at this and go, I don't know if I've got the answer or not. So it's nice to look at a picture. So if I go to the left 2, I have to be down 2. If I go to the right 5, I have to be up 5/8. This isn't to scale, but any continuous function I draw between these points, again, it doesn't have to be differentiable, so I can have these little cusps and corners. Any continuous function I draw between those points must cross the x-axis, which is where y equals 0. So because we have continuity, and because f of -2 is less than 0 is less than f of 5, because the y value falls between the y values of the endpoints, I can guarantee there is a point where it's guaranteed to be 0. Now if I go ahead and compute this, I'm going to set x over x plus 3 equal to 0, multiply both sides by x plus 3, and you get x equals 0. 0 is in fact within -2 and 5, so the c value that I want is 0. Alright, next series of questions we're going to look at a table of values for two differentiable functions. When you see the word differentiable, you should also think of continuity. So these functions are also continuous. Now the first one, I'm looking at h prime of c. So I need to focus my attention on h, and I need to realize that h prime, a derivative, is going to deal with, you guessed it, mean value theorem. In this particular case, it would be Rolle's. Now I already have the continuity, I have the differentiability, so I am allowed to apply Rolle's provided that I can find 2 points where the y values are the same. Well, I've got a y value of 6 right here, y value of 6 right here, so at -4 and 2, somewhere in between those 2 points, I should be able to find a slope equal to 0 because my endpoints have that value. Any continuous function I draw between these points, continuous and differentiable, is going to have some points, one or more points, where the slope is 0, the instantaneous slope, the derivative. Alright, so the next one, we're looking at g prime of c equal to -1, so we're going to focus on g now. And now, since it's equal to -1 and not 0, this is specifically mean value theorem. So I need to find some points where I can find an average slope, so my f of b minus f of a over b minus a needs to be equal to -1 somewhere. Well, we're in luck. So if we look at these points and we compute the change in y over the change in x, we end up with -9 over 9, which is really just -1. Now you could also notice that this also applies on the interval -1 to 2. So either within the interval -4 to 5 or the interval -1 to 2, we should find a point C such that its derivative is -1. So you could do the math on the red one using these y values. You can just see that the y and x values got flip-flopped. So anytime you have something over the opposite subtraction problem, you're going to get -1. So we luck out with both of those intervals. Alright, so the next problem, we want to guarantee that we get a y value of 0. So now we're not looking at a derivative. We want a y value to be 0, and we're going to focus our attention on h. So we should be thinking of intermediate value theorem. Now for this, we need to find y values that go from positive to negative. So the first one we see is from 6 to -2. So the interval -4 to -1, we could be finding a h value equal to 0. And then also on this interval here, from -1 to 2. So those are the two intervals that we could expect to find a y value of 0. Now some of you might ask, why can't I go from -1 to 5? You could, but more specifically, it's going to be somewhere between -1 and 2. This function very well could have another 0 between 6 and 7, but we do not have enough, between 2 and 5, x equals 2 and x equals 5, but we don't have that information, so we cannot say that because we don't have a negative value on either side. But it might happen, we just don't have all that information. So these are the only two we can guarantee because we have a change from positive to negative and then back to positive if we were to graph this. So those points are roughly there, again not drawn to scale. You'd have to cross somewhere between here, and you'd have to cross again somewhere between here. So those two intervals, we have a guaranteed value of h of c equal to 0. Now the last one, what value of the derivative are we guaranteed? So now we've got a composite function, we've got an interval specified. So what I'm going to do is I'm going to compute the value of the function at each of those endpoints. Now again, this function is going to be continuous and differentiable because it is a composite function of two differentiable functions. So we can guarantee that. So we are applying mean value theorem. So we go ahead and plug that into our function. So we find g of -1 on our table. We find that that's 2. So we're really computing h of 2, which is 6. And then we are computing g of 2, which is -1, so then h of -1 is -2. So plugging into our formula, we should find some point between -1 and 2 such that f prime of c is equal to change in y over change in x. We get a value of -8/3. So somewhere in between x values of -1 and 2, we can find a point where the slope, the instantaneous slope, the derivative is -8/3. So if we had a function, an explicit function for f of x, we'd take the derivative and set it equal to this -8/3. All right. Last problem before we dive into some multiple choice. Is a prime of x guaranteed to be 0 given the application of Rolle's theorem? So the first thing we want to check is continuity. This function is continuous at every value. Notice that it's a third root function. So anytime you're taking an odd root of values, you can take odd roots of negative numbers. So we don't have an issue like with the standard square root where everything in here has to be positive or equal to 0. So we can take on all values. But if we take the derivative of a of x, so a prime of x is equal to 2/3 x plus 5 to the -1/3. So we move that to the bottom. And you should immediately notice we can't divide by 0, so x equals -5. We would be discontinuous there, and that is in our interval. So we cannot apply Rolle's theorem. Some of you may be tempted when you see Rolle's theorem to immediately plug in those endpoints, and I can tell you if you do plug in -6 and -4, both of those values will give you the same answer, because when you take the cubed root and then square it, you'll get the same result. So -6 plus 5 is -1. Take the cubed root, you get -1. Square it, you get 1. Do the same thing for -4, you also get 1. So sometimes your temptation is to apply it. If you were to graph this function looks something like this. So this would typically be the point where you would expect that slope of 0, but in this case it is not differentiable at that point, -5. Alright, so now let's dive into some multiple choice questions. These all come from some old tests, and they have some great properties that come up as we look at the correct answers and the wrong answers. So the first one says let f be a function that is continuous on the closed interval. So when you see continuity, do not think anything else other than intermediate value theorem or extreme value theorem. But in this case, it tells us to explicitly use intermediate value theorem. So what I would do is do a very, very basic sketch. So if we go to 2, 4, this function is going from 10 up to 20. So intermediate value theorem tells us that we can hit every value between 10 and 20. So we read option A. It says f of x equals 13 has at least one solution in the open interval 2 to 4. That is exactly what intermediate value theorem. It tells us that we will hit every value between 20 and 10. So we most definitely will hit 13. The second option, f of 3 equals 15, way too specific. Intermediate value theorem does not give us the specific location where we take on the y value. Way too specific. The last one, f attains a maximum. That is certainly true. It will attain a maximum, but that's not by the intermediate value theorem. That's by the extreme value theorem. So that can be a misleading option if you don't remember your theorems. The next one, f prime of x equals 5, has at least one solution in the open interval. So some of you might have done 20 minus 10 over 4 minus 2 and seen that that was 10 over 2 is 5 and gone, that's a reasonable solution for this problem. But that is mean value theorem. So again, if you forget your theorems, that is a very misleading option. And the last one says f prime of x is greater than 0 for all x in that interval. Well, I can tell you right now, I'm going to draw a continuous function that does this. That is continuous, and I have multiple locations where it's going down. I go down here, and then a little dip at the end. So I can certainly draw something that is decreasing, but still ultimately goes up from 10 to 20. So that one will not work. All right, next questions. Again, we've got a continuous function, and again, we have intermediate value theorem. So I highly recommend you plot these points. So at -1, and we go all the way up to 3 when we are at x equals 6. So we are going to be able to take on every value. Intermediate value theorem says we'll take on every value between -1 and 3. Okay? And actually that would be inclusive. I could put close brackets. So let's take a look. F of 0 equals 0. That's a lot like the last question. That is way too specific. We cannot guarantee that. The next one says f prime of c equals 4/9. You should stop reading that f prime of c because that's telling you something more like mean value theorem. It's got a derivative. We're just looking for a y value. The next one says that f of x is less than or equal to, which if I correct my brackets like I said before, for all x between -3 and 6, that is tempting, but like I drew on the last picture, this thing could dip and dive and go above and below. It can do everything it wants in between. It can go outside of this window from -1 to 3. We're just guaranteed to get some value in between there, given a continuous function. So this is not going to happen. It can go outside of that range as well. The next one, it says f of c equals 1 for at least one c. Well, 1 is within the y values of -1 to 3, and it's going to happen on some x values -3 to 6. That's the original interval. This is the correct answer. The next one is very misleading. F of c can equal 0. That is true because that falls within the range of -1 to 3. These are my y values. But this is referring to -1 and 3, which are the y values, not the x values. So when I look at between, I want to see some domain, some x values going on. So this one would be incorrect because it's referencing the wrong x values here. These x values are actually my y values. Alright, so on this last one on this little page, it says g is a continuous function on the closed interval, and it gives me some points. So I would plot these points. I've got g of 0 equals 1 and g of 1 equals 0. It's a continuous function, so it can do anything it wants in between these 2 points, but I'm going to have every y value between 1 and 0, so I will hit all these values, including the endpoints. Okay. It says, which of the following is not necessarily true? Make sure you underline or circle that when you see questions like this on your test. So I'm looking for things that are false. So option A says there exists a number h in that interval 0 to 1 such that g of h is greater than or equal to g of x for all x values in that. Well, what is this really saying? It's saying that somewhere I have an absolute max. Now, absolute max comes from extreme value theorem. Extreme value theorem, the one condition I really need to satisfy is continuity, which I have. So this one is true. I will have an absolute max somewhere. The next one says for all a and b in that interval, if a and b are the same, then their y values are the same. This is true for any function. This is the definition of a function. Remember, it's got to pass the vertical line test. So if I plug in the same x value to a function, I should expect to get the same y value out. The next one says that I should have a y value of 1/2. Well, 1/2 is within the range from 0 to 1. So this one is absolutely true based on the intermediate value theorem. Now the next one says that I should get a y value of 3/2. Well, 3/2 is up here. I am not guaranteed that given the y values at my endpoints, because 3/2 falls out of that. So this would be the true statement. Okay? So on the last one, it is true. This one is simply the definition of continuity. So you should recognize this from continuity. All right. Next problem. Right, we've got a table of values. It says the function is continuous. It says, has the values given in the table below. The equation f of x equals 1/2 must have at least two solutions in the interval if... Okay, so if we plot these points, so at 0 we have a value of 1, at 0 we have a value of 1, at 2 we have a value of 2, and at 1 we have some unknown value. So in order for us to have two solutions at least, at 1, at x equals 1, we need to dip down below, we need to dip down below 1/2. So I need to look for a value that is less than or equal to 1/2. So not less than 1/2, not less than 1/2, not less than 1/2, not less than 1/2. There's my answer. Okay. So again, since I need the y value, I need to guarantee a y value of 1/2, I have to be somewhere below y/2 since the y values given to me, 1 and 2, are both above it. So this is using intermediate value theorem. So again, I needed to have f of 1 needed to be less than 1/2, strictly less than. Next one, f is a differentiable function. That means I also have continuity on the interval 1 to 10. Gives me some points. I'm going to plot those points. So I got 2, 5, and 9. At 2 I've got -5, 5 I've got +5, and at 9 I've got -5. So immediately, since I knew I plotted the same y value twice, I should probably be thinking Rolle's theorem at some point. Now, one of them says f has at least two zeros. I'm looking for which ones are true. That is true because I'm going to have to cross somewhere between here, and I'm going to have to cross somewhere between here. Now, those two blue lines I just drew would not make a differentiable function, so please do not pretend that is my function. The next one says the graph of f has at least one horizontal tangent. That is absolutely true because of Rolle's, like I said at the start. So since I have the same y value at 2 and 9, that is true because I have continuity, differentiability, and I have f of a equals f of b. So the first one came from IVT. Roman numeral 2 is Rolle's theorem. Next one says that I have some point where y equals 3. Well, I go all the way up to y equals 5, and I start down at -5. I'm definitely going to hit some value of 3 in between. So that is true by IVT. So all three are true. Alright, next one. It tells me explicitly to use mean value theorem. Mean value theorem tells me plug in the endpoints. So I'm going to do f of 3 minus f of 0 over 3 minus 0. If I compute that, I get 0 minus 0 over 3, which is 0. So this is technically a Rolle's theorem problem. Not that that matters. That's just a specific subset of mean value theorem. So I need to compute my derivative, which is 3x squared minus 6x, and I need to set that equal to 0, the 0 that I got from my average rate of change between the endpoints. So when I set that equal to 0, I factor, and I get 3x times x minus 2. So I get 0 and 2. Now, none of these options have 0 and 2, which is very nice of the AP test makers, but since 0 is an endpoint, I would not actually use 0. So the only option to choose is 2. So again, I have to find some point within the open interval 0 and 3 where the derivative equals 0. So I do not include 0. Next problem, very similar, mean value theorem. So I'm going to compute f of my endpoints, f of 3 pi over 2 minus f of pi over 2. And the separation of those two is just pi. This turns out to be square root of 2 over 2 minus root 2 over 2. If you remember how to evaluate sine of 3 pi over 4 and sine of pi over 4, those both have the same value. So this is 0. So this is more specifically a Rolle's theorem problem. So I'm going to compute my derivative. So f prime of x is equal to cosine of x over 2 times 1/2 from chain rule, and I've got to set that equal to 0, that average rate of change between my endpoints. So ultimately I can divide both sides by 1/2, and I'm trying to solve where cosine of x over 2 equals 0. So cosine equals 0 at pi over 2, 3 pi over 2, yada yada yada. But I have to ultimately multiply that result by 2. So if I multiply these by 2, I'm really looking at the values of pi, 3 pi, 5 pi, etc. Now I have to be within the interval pi over 2 to 3 pi over 2. The only one that satisfies that is pi. Quick check, I plug pi into my derivative down here. Cosine of pi over 2 is 0. And I'm done. 0 times 1/2 is 0. Alright, the next one. F is a continuous function, so I should note that it's continuous and differentiable on the closed interval. And I've got table values. Which of the following must be true? The minimum value of that is 2. Nope. I cannot be specific and get the minimum value because, sure, I look at this and see 2 and I think, oh, that's the smallest number. But I don't have all the information in this table. Next one says maximum value is 4. Again, I don't have all this information. Next one says f of x is greater than 0 for all the x values between 0 and 4. I don't have all the information. That's way too specific. Next one says that the derivative is strictly decreasing, the function is strictly decreasing, or the derivative is strictly negative on the interval 2 to 4. Sure, it's tempting to look at that and say everything's decreasing, but again, I don't know what's happening between 2 and 3. Even though it's going down, it could initially go up and then go down. Way too specific. So I'm ultimately, process of elimination, left with that one. And I know this because if I look at f of 0 and f of 4, they are the same. So because this function is continuous and differentiable and the endpoints 0 and 4 have the same y value, Rolle's theorem. So I get that the derivative has to be 0 somewhere between those points. Alright, next problem. Alright, so I've got a continuous function and differentiable. I've got both things I need. Which of the following statements could be false? So if I do a rough sketch, I'm going down from -5 up to 4. Right, so the first one says there exists a C, again I'm looking for false answers, where I have a y value of 0. Well, that's guaranteed by IVT because that 0 falls between -5 and 4. So that is true, so I'm going to cross that one off because I'm looking for false answers. The next one says I can guarantee that the derivative is 0. Well, I don't have that f of a equals f of b for this particular interval of -2 to 1. That would be Rolle's theorem. I cannot apply that here. I don't have the information necessary for that. So that one is actually the false one. Let's see why these next ones are true, though. The next one says I can guarantee a y value of 3. Right? That is true because 3 is within the -5 to 4 range. So that one is true by IVT, Intermediate Value Theorem. Next one says I can get a derivative of 3. F prime of c equals 3. So that's going to be a mean value theorem. If I compute the slope from these 2 points, I end up with 9 over 3, which is 3. So I can guarantee that. And then the last one says there exists a C, blah, 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 where f of c is greater than or equal to f of x. That's saying I have an absolute max somewhere. And because my function is continuous, I can guarantee that by the extreme value theorem. So continuity gives me an absolute max on the interval. Alright, next one. If f of x is continuous and differentiable, which of the following could be false? Alright, the first one, continuous, differentiable, the first one is true because this is simply the definition of mean value theorem. The next one says f prime of c is equal to 0 for some c such that yada yada yada. That one is false. That is the false one. I do not have the information that f of a equals f of b. The last one says that I have a minimum. Sorry, the next two say I have a minimum or a maximum. Those are true because I have continuity and I can apply the extreme value theorem. All right, very last problem. Show that the instantaneous rate of change is the same as the average rate of change on the interval 1 to 4 for for this function x plus ln of x. So you should be thinking mean value theorem. So I'm going to compute f of 4 minus f of 1 over 4 minus 1. Plug in 4 and I get 4 plus the natural log of 4. Subtract, make sure you put these parentheses. I'm going to get 1 plus the natural log of 1. Now the natural log of 1 is 0, so I'm going to cross that off. And I get 3. So I got 4 minus 1 on top, which is 3. So I've got 3 plus the natural log of 4 over 3. If you wanted to, you could rewrite that as 1 plus 1/3 the natural log of 4. Oops. There's my wonky 4. Alright, so I need to take the derivative of this function, f prime of x, which will be 1 plus 1 over x. And I have to set that equal to 1 plus 1/3 natural log of 4. So you can see why I rewrote it like this. Because now my 1's cancel, and I just need 1 over x to equal 1/3 the natural log of 4. Solving this, I get x equals 3 over the natural log of 4. This would be a calculator problem based on these decimal answers. I get 2.164. So again, I found the average rate of change by computing the slope between the points 1 and 4, computing, of course, their y values, so change in y over change in x, and then I set the derivative equal to that value and solved for x. Thank you for watching. Stay tuned for a video on optimization and position velocity acceleration problems.